Hello, math students. Welcome to Distance Learning with Lee, where I make learning mathematics super easy. On today's video tutorial, we are going to be going through the properties of a quadratic function. All right, namely the domain, the range, the vertex, which is also called the turning point, the axes of symmetry of a quadratic function, how the nature of the roots of our quadratic function can help us in determining the shape, and the minimum and the maximum value of a quadratic function. Before we get started with the video tutorial, please make sure that you are subscribed to the channel if you're not. And also make sure that you hit the notification bell to make sure that you get notified every time I upload a new video. Okay, so let's get started. So when working with a quadratic function, right, it will normally be given to you guys, obviously, in its standard form, ax squared plus bx plus c, or in the form of, so it's that, or in the form of f of x is equal to a x plus p all squared plus q, right? So those are the two different ways that the quadratic function will be like represented in your tests or your exams. Okay, so firstly, it's very important to when obviously when you're given a quadratic equation and you're trying to determine the shape of that quadratic function, you need to take note of the a value, right? So your coefficient of your x squared, and see whether it's a positive or if it's a negative, right? So if you look at the screen here, right, if your a is greater than 0, then it tells you that your quadratic function is going to open upwards. If your a is less than 0, it tells you that your quadratic function is going to open downwards. Okay, so the a value tells you about whether your quadratic function is going to open upwards or if it's going to open downwards. Okay, another thing that is very important to know is the domain of a quadratic function. What does domain mean? Domain means a set of your possible x values, right? So if you were to look at your quadratic function, right, particularly this one or this one, right, we can see that there are no restrictions on our x-axis, right? The function starts from negative infinity in our x values for this quadratic function starts from negative infinity and it goes all the way to positive infinity. So there aren't really any restrictions for our quadratic function on the x-axis, right? So the domain for your quadratic function is going to be x is an element of real numbers. Okay. What about the range of our quadratic function, right? So when you look at these two functions that I have here on the screen, right? When you look at where our a is greater than 0, right? The y values start from 0 and they go all the way to positive infinity. So that is our range, the y values. We do have restrictions in this case on the y-axis because it starts at 0 and it goes all the way to positive infinity, right? And in this case, our range, it starts at negative infinity and it stops at 0, right? So that is the range of this function. And the range of our functions, our quadratic function, is represented with this notation here that I have on the screen. Okay, and then the minimum and the maximum value of our quadratic function. If you look at this shape here, right, we can see that this function is a minimum because we've got the lowest, it represents the lowest value that you'll get for this quadratic function, and the lowest value of the y that you'll get for this quadratic function is 0, right? And in this case, this is a maximum, right? Because the highest value that you can get for this quadratic function for the highest y value that you'll get for this quadratic function is 0, right? So it's a maximum. And another thing that's also very important when working with your quadratic function is being able to determine your axes of symmetry and your turning point, right? Let's start off with your axes of symmetry. What are the axes of symmetry? The axes of symmetry is an imaginary line that divides a graph into two mirror images of each other, right? So if you look on the screen here, okay, and obviously you are given a quadratic function that looks like this, right? What would the axes of symmetry be? We said that the axis of symmetry R is an imaginary line that divides a graph into two mirror images of each other, right? So the imaginary line that divides this graph into two mirror images of each other is a line that goes through this point here, right? Right? So that is our axis of symmetry. And the equation to determine your axis of symmetry is given by x is equal to minus b over 2a. So this equation is going to give you this line that cuts your graph into two equal parts. Okay. And then what is the turning point of our quadratic function, right? The turning point is that point there, right? And it is defined as the point at which a graph reaches its maximum or minimum value and changes its direction, right? So in this case, we know that we can see that this graph is a minimum, right? And this point is where this graph changes, right, its direction. So it reaches its minimum point and then it changes its direction, right? Therefore, this is our turning point of our parabola. Okay, let's just go into like some practical examples so that you guys are able to put everything into perspective. Okay, so let's say you're given an example like if of x, which is equal to x squared minus 5x minus 6, right? The first thing we need to determine is obviously the shape of this parabola. We can see that your a value is 1 and it is greater than 0. Therefore, we can already see that we are going to have a smiling parabola. We've got an a value that is greater than 0, so we're going to have a happy parabola. That's the first thing we need to get, all right? Second thing we need to get is obviously the axes of your symmetry. How do you get the axis of symmetry? We use x, which is equal to minus b all over 2a, right? So what is our b? Our b is the coefficient of our x, right? And then our a is your coefficient of your x squared. So it's minus, your b is minus 5 all over 2, your a is 1, right? So we find that our axis of symmetry is 5 over 2. Okay. That is our axis of symmetry. Okay. What else can we find? We can find the turning point of this parabola, right? We can find the turning point, right? So how do we get the turning point? We said that the turning point is determined by just going back to just rewriting the equation here, f of x, which is equal to x squared minus 5x minus 6, right? So to get your turning point, we've already found that our axis of symmetry is equal to 5 over 2, right? Our axis of symmetry. So all we need to do is we need to substitute that axis of symmetry into our equation to find the y value that goes with this x, right? So it's 5 over 2 all squared minus 5 over 2 minus 6, and that gives us a minus 49 over 4, right? Therefore, we can conclude that our turning point for this parabola is 5 over 2 and negative 49 over 4. Okay. What else can we get? What would the domain be? Okay, but before we get the domain, let me just quickly just sketch this graph, because we've already determined the turning points for this graph, and we found that it is 5 over 2 and negative 49 over 4, right? So let's find your x-intercept and your y-intercept. How do you find your x-intercept and your y-intercept, right? So to sketch your graph, this is what you do, right? You find your x-intercept and your y-intercept. So you're going to let your x equal to 0, right? So if you let your x equal to 0, what happens? f of x, which is equal to x squared minus 5x minus 6. If you let your x equal to 0, what happens? Okay, 0 all squared minus 5, 0 minus 6. You get your y to be equal to minus 6. Okay, so if you x is equal to 0, if your x is equal to 0, your y is equal to minus 6, right? And then let's let our y equal to 0 to see what we get. So if you let your y equal to 0, you get x squared minus minus 5x minus 6. Okay, we can just simply factorize this by using the method of inspection. So it's going to be x, it's going to be x, it's going to be a minus, it's going to be a plus. Factors of 6 that when a plus or minus them will give me a minus 5. So it's minus 6 and plus 1. Therefore, we can conclude that your x is equal to positive 6, or your x is equal to negative 1, right? Therefore, if your x is equal to 6, your y is equal to 0, and if your y is equal to 0, your x is equal to negative 1. Okay, guys, so we found all the important points that we need to draw our graph, right? So now we're going to use them in drawing our graph. Okay. So let's do that. Okay, I'm just going to use this graph quickly. So it's going to make our lives very, very, very easier. So obviously we said that our graph is x squared minus minus 5x minus 6. Okay, let's see how our graph is going to look. All right. Okay, so that's how our graph is going to look, right? Okay, I'm going to put my pointer here. We said that our x, we've got an x value of -1 there, right? And then here we had another x value of 6 and 0. Well, x value was 6 and the y was 0. And then here we had a y-intercept of -6. And then we also got our turning point here, which is 2.5 and -12.5. Right? So that is how your graph is approximately supposed to look like. I just used this awesome feature because I just want to quickly move through this. Okay. And lastly, guys, I think I've actually right, let me just go through this quickly again. So I've just discussed the important things that you need to know about the shape, the domain, the range, the maximum. All right, cool. So let's just go through the domain, right? The domain. So we've already determined how our graph is supposed to look like. Let's just write down the domain for this function, right? We said that the domain for this function is a set of possible x values. There are no restrictions for this function on our x-axis, right? There are really no restrictions. So you can say that your domain is your x is an element of real numbers, right? And then let's look at our range, right? Let's look at our range, right? We found that, remember that we found that our turning point was equal to 5/2, which is your 2.5, and -12.25, right? That is what we found for our thingy, for our turning point, remember, right? So our range is going to be -12.25, and that goes all the way to positive infinity. Okay, so that is going to be the range for our function. Okay, it starts at -12.25, right? This is where our graph stops, and it goes all the way to positive infinity. So that is our range. Okay, we also see that our function is it's a minimum, right? Because it has the lowest y value that you can get is -12.25. This function is not a maximum. It doesn't have a maximum y value. Okay, we've got a minimum y value of -12.25. Okay, so I'm just gonna write that down quickly for you guys. All right. Okay. So we said that our range is -12.5, and it goes all the way to positive infinity, right? And then this function is right, and the minimum value is -12.25, right? Is the lowest possible y value is the -12.25. Okay, I think I've actually gone through everything, right? I think I've gone through everything. Let me just check here, right? So we've obviously discussed the different properties of a quadratic function that we'll be going through: the domain, the range, how you get the domain and the range of the function, how you get the vertex, which is the turning point, how you get the axis of symmetry, which is an imaginary line that divides your graph into two equal parts, right? And how you determine the shape of a function, whether it's going to open upward or whether it's going to open downward, right? I'm also just going to quickly go through how the nature of roots is going to help in determining the shape of your graph, right? Let's just quickly go through that together. Right. Remember, guys, when you're dealing with a quadratic function, it is obviously going to be usually given to you guys in the standard form of ax squared plus bx plus c, or in the form of a open bracket x plus p close bracket all squared plus q, right? Right? So if it is given in this form, you can also just be able to determine how approximately your graph is going to look like, to see when you have to sketch it if you're doing the right thing. Right. So obviously you get your real roots, right? And obviously if you're given your quadratic equation in the form of y, which is equal to ax squared plus bx plus c, right? And if you guys remember, we can use the quadratic formula minus b plus or minus b squared minus 4ac all over 2a to get your x-intercepts, right? So your real roots, right? If you just focus on what's under your square root sign, right? If we just focus on your value that is under the square root sign, right? This, right? If this value is greater than 0, right? If this value is greater than 0, this means that you will have two x-intercepts, right? So your graph will have two x-intercepts, right? So you'll have an x there, an x-intercept there, and then obviously there. Your graph will probably look something like that. Right. So if the bx squared, if your bx squared, your b squared minus 4ac is greater than 0, then it'll tell you that you've got two x-intercepts, right? Okay, and depending on whether your a is a positive or negative, that will tell you whether your function is supposed to be downwards. Okay, and then if your b squared minus your 4ac is equal to 0, right? It tells you that if you've got like equal roots, right? That tells you that there is only one y. There's only one x-intercept, right? There's one x-intercept. Right. Function will probably look like that, right? Right? So your function will probably look like that, or like that. Okay, the y-intercept, right? And what happens if your b squared, what happens when your b squared minus 4ac is less than 0? That tells you that you've got non-real roots, okay? And that means that there are no x-intercepts. Okay, there is Therefore, at this point, it's just like drifting in space. Okay, so it's a, right, or something like that, right? And obviously, depending on your value that you have for your a, that will tell you whether your function will open upwards or downwards. Okay, I'm just going to do a quick recap for this session because I am going to be finalizing my paper 1 past paper that I'm currently going through with you guys. So this is going to help you guys with just analyzing the questions there. Okay. So obviously we went through the properties of a quadratic function. We said there's the domain, range, vertex, axis of symmetry, how the nature of the roots can help you determining the shape, and also just determining the maximum or minimum values of a function, right? If your value of a is greater than 0, your function opens upwards. If your value of a is less than 0, your function opens downwards, right? We said that in terms of your quadratic function, really there's not really any restrictions in our x-axis, so any element of real numbers. With your range, it is important to look at obviously your sketched graph to see where you have a minimum value or you see where you have a maximum value, and that will guide you whether where or how your function starts. In this case, we said that your minimum value for y that you'll get here is 0. Therefore, it starts from 0 and goes all the way to positive infinity. And then in this case, your your maximum value for y is 0. So your function will start from negative infinity and it will go all the way to 0. Right. We also said that when you have a maximum value for y when your a value is less than 0, and you have a minimum value when your a value is greater than 0. So your quadratic function will be a minimum when your a is greater than 0, and it will be a maximum when your a is less than 0. Okay. We looked at a couple of examples where I also explained what the axis of symmetry is. And we said the axis of symmetry is an imaginary line. It's an imaginary line that divides a graph into two mirror images of each other. We find axis of symmetry by using the equation of x is equal to minus b over 2a. All right. And this also obtained from your quadratic function, and we define the turning point as a point at which a graph reaches its maximum or minimum value and it changes its direction. Once we found the axis of symmetry, it will be very easy to find the turning point because your x is going to be the x value for your axis of your turning point, and you substitute that x value into your equation to get the y value of your turning point. Okay. We looked at a practical example where I just basically reinforced what I was meaning with the whole axis of symmetry, right? And with this particular function, we found that the axis of symmetry is 5 over 2, right? Okay. We found that our turning point, therefore, is equal to 5 over 2 and negative 49 over 4. All right. We also sketched the graph, and to sketch the graph, I told you guys that it's important to start off by letting your x, to be equal to 0, and letting your y to be equal to 0 to get the x-intercepts and the y-intercepts. We found that our x-intercepts was 6 and negative 1, and we found the y-intercept to be equal to negative 6. Okay, I drew the function, right? And we could see here that we do in fact have a turning point of negative 12.25 as our y, and then our x, which is 2.25, and then I showed here the x, we had a negative 1 and a negative 6 there. We see that this function is a minimum because the lowest y value that we'll get is negative 12.25. And then in terms of our domain for this function, we don't really have any restrictions on our x-axis because our x starts from negative infinity and goes all the way to positive infinity. We can see here. So x is an element of real numbers. And then that is it, guys. I hope you guys enjoyed the lesson. I will be just also doing a summary of the hyperbola, and then from there I will upload the mathematics paper 1 November 2020 exam, finalizing everything, and then I'll be starting with my paper 2 preparations, because you guys are writing on the 3rd of, is it the 3rd? I think 5th or 3rd of November. I'm not sure. Right. Happy studying, matriculants and grade 11s and my grade 10s. And I'll see you guys on my next upload. Goodbye.